Yeah, thanks. So I am here today to talk about stirring by rising bubbles. But before jumping into my talk, let me thank the organizers of the program, Amit and Professor Guha, for this wonderful opportunity, to stay over here and carry out a project for about 2 months, which I thoroughly enjoyed. And I'll start with the acknowledgement first because I don't want to rush it through towards the end. So this work was done, is still being done, it's an ongoing project with Professor Jean-Luc from University of Wisconsin. He was a really a nice guy. I mean, I was very fortunate to meet him. He's a very inspirational researcher, and his passion for research is very infectious. And Vishal was here, of course, to have a stimulating discussion and all. So thank you for that.
And you're taking all your time.
All right. So the topic, of course, is, like I said, stirring induced by rising bubbles. A bit of motivation to be in line with the theme of this program. If you look at ocean, for example, there are many swimmers from whose size ranges from micro scale to macro scale. And there are reports which actually claim that about 30 to 40% of mixing that's happening in ocean is due to these swimmers, and which ultimately leads to oceanic turbulence as well. So this work was actually partly done by Jean-Luc himself. So we are asking in similar lines the question as to how a bubble, the stirring and mixing induced by a bubble. It has technological applications as well. For example, in chemical reactors, bubbles are actually used to induce mixing and absorption and stuff like that. So, we are asking the question, so if there's an infinite fluid medium, and if there's a bubble rising, what is the stirring caused by this bubble? So we need to solve the velocity field induced by the bubble in the fluid, and the momentum equation in the fluid, if we assume very viscous fluid, so the Reynolds number is practically nil, we'll have the Stokes equation, where we have balance between the viscous force and the pressure force, and we can have a forcing term as well, which can be a function of force. And this is the continuity equation, which says that the divergence of velocity is 0. And how do we model the bubble? So if you imagine a sphere moving through a fluid, the fluid will exert a drag force on the sphere, and Newton will tell you that the sphere will exert an equal and opposite force on the fluid. So as far as the fluid is concerned, it will see the sphere as a source of force, a source of momentum. And the first order of approximation is, of course, a finite, point particle limit, where the force will be a point force. So the spatial function, the force over here, will become proportional to delta function that is situated at the position vector capital R. And F is, of course, a drag force. And in the case of sphere, this will reduce to 6 pi eta v, 6 pi times viscosity times the diameter of the sphere times velocity, which is the famous Stokes drag force. And the solution to this exists, and it is given by this expression here. And as you can see, the velocity actually scales as 1 over r, which is the characteristic of a point force source. And this actually leads to the definition of Oseen tensor, as given by this expression here. So this is the problem we are trying to analyze. So imagine an infinite fluid, and at z equal to 0 plane, we have an area earmarked for the release of the bubbles. So the bubbles are released randomly, and we look at a fluid particle in the fluid medium anywhere and ask how much it gets displaced. Why we're interested in displacement, that will lead to the definition of the effective diffusivity of the problem, right? So because the variance of the displacement will give you is equal to 2 times the diffusivity times time, in a Brownian motion sense. So that will lead to the definition of effective diffusivity. And so before moving to many bubble situation, let's understand what one single bubble will do to a fluid particle. So in that case, all that matters, so the fluid is rising vertically up. There is no transverse motion. So all the dynamics is confined to a plane containing the line of rise of the bubble and the fluid particle you are considering. So it's an axisymmetric problem. If you go around the line of rise of the bubble, nothing will change. You'll get the same picture, and it's an axisymmetric problem. So let's consider one such plane and call it my xz plane. I mean, so y coordinates are all 0 in my case. And small r is a position vector of the bubble, and capital R is a position vector of the, small r is a position vector of the fluid particle I'm considering, and capital R is a position vector of the bubble. So these are the initial conditions at time equal to 0. So this is the fluid particle is at position x0, z0, and r is released from some x0 and z equal to 0. And at some time, at some later time, x0 will become x and z0 will become z. And the bubble x0 won't change because it doesn't have any transverse motion, and z will keep on varying with time because it's rising with a terminal velocity of capital V. So plug this into the Gaussian tensor and we can solve the x and z component of velocity of the fluid particles, and this is the expression. It's a coupled nonlinear expression, and we have to solve it numerically. But we can do some analytical solution to this, assuming that the x and z appearing on the right hand side does not change with time, or in other words, it's always x0 and z0. So then the right hand side will be only a function of time, and we can integrate to get these expressions for the displacements. So as you can see here, these displacements are only a function of the x0 minus x0, which is the relative position of the fluid particle from the bubble in the x direction, and z0, which is the relative position of the particle with respect to the bubble in the z direction, which makes sense, right? I mean, if you're a fluid particle, all you care is how far you are from the bubble. I mean, the actual origin you put, it doesn't matter. Here also we can actually prove this, that there's a translation invariance, but it's very clear from this expression. And the net displacement is what I call as a drift. So if I plot this, so for a given z0 and ρ0, we can actually evaluate drift. So we can get this curve, and the blue curve here is the numerical result I observed by numerically solving the expression for the velocities, and the black curve is the theoretical curve. And as you can see, they match, they agree with each other fairly well. And as you increase ρ0, we can see the disparity between the curves actually comes down, which is expected because the theoretical is based on far away approximation, where we say actually x and z not change much. Okay, so we are dealing with Stokes equation, which is a quasi-steady equation, which means the time is not explicitly appearing in the equation. So the solution to this equation is dependent only upon the boundary condition and forcing at that particular instant, or in other words, information travels very fast. So one way to deal with this singularity is to actually put a wall and introduce a natural length scale to the problem. So that's what we did here. We actually introduced a side wall, a planar wall in the problem, in which case we had to actually add an image force and some dipoles to actually enforce no slip and no penetration boundary condition at the wall. And in that case, we will have the expressions for velocities as given by these two equations. I'll play a movie here. Okay, so this is the wall we have at x equals 0 plane, and this is the bubble rising. And we look at a fluid particle at this location, and the red curve here actually shows the trajectory of the fluid particle if there were no wall. And the blue is actually in the presence of the wall. And as you can see, the blue actually comes to a stop after some time, whereas red actually keeps on going. So this is what I'm talking about, because we have a singularity there, and since it's Stokes law, the viscosity is so strong that at all time, it's present. The presence of the bubble is felt by the fluid particle, whereas in the presence of wall, some sort of drag force acts, and it actually comes to a halt. So this kind of mitigates the singularity that we are dealing with. So here we have plotted the drift as a function of, again, ρ0 and a given z0 in the infinite fluid medium where we don't have any wall, and a semi-infinite fluid medium where we have a wall. And as you can see, with the wall, actually the drift comes down drastically. And if you actually simulate for longer time, actually this drift actually blows to infinity because we have a singularity there. And now with more bubbles, what we have is, if we have m encounters, we have encounters with m bubbles, for example, the net displacement of the particle can be written like this. I mean, the initial position vector of the particle plus the summation drift due to all the bubbles. And if you take an average over this, because we don't know the actual position of the bubble. Bubble is randomly distributed. We'll get an expression like this. And for a given time, the number of bubbles in the system is given by A times velocity of the bubble times the number density of the bubble times T. And then we give a probability distribution as a function of X and Y. I mean, the initial location of the bubble. And so we take this average will become an integral over this area, and we can actually define V drift. So this is something that I have to do in the future. And of course, if you take the variance of the displacement, we can define an effective diffusivity in terms of drift. So the next order of business is to actually find out this matrix, the drift as a function of rho and z. This is the conclusion. So we have actually formulated the problem, and the drift function was actually evaluated in an infinite fluid medium due to a rising point particle limit, and we actually solved the asymptotic solution as well in the limit of faraway field, and we got very good agreement between the two. And the presence of sidewall is actually found to actually remove the singularity from the problem. And other wall configurations also we are trying. I mean, we are trying to do other different confinements, like top wall, bottom wall, then top wall with free surface and stuff like that, which are all work under progress. Right. Coming to answering your second question first. So the reason, I mean, we can of course explain using the equations, but the reason would be actually, you can imagine if there's a wall present, it would in fact cause a boundary layer, right? So it induces more drag, and essentially the fluid particle has to come to a halt. Yeah, its effect will come down. Yeah, it will come down. Yeah. Yeah. Depending upon how far it is. Yes. Yes. Right. Right. Yeah, effective diffuse. So that comes from a scalar. Yeah, like I said, if you compare with for example, what people have reported is the effective diffusivity due to the swimmers is about 100 times compared to the thermal diffusivity. Yeah, so we don't have any numbers as of now, so I have to evaluate that to give you a comparison. Yes, except that there is no convection. Yeah, it's only due to.
Number one is basically when you look at this mixing and stirring.
Right.
But here you start with the Stokes.
Yes.
Stokes is basically low Reynolds number.
Right.
So it's a micro swimming.
We believe that mixing will be more. Okay, we started with Stokes flow because we have nice solutions to. Yeah. So again, for comparison, I need to do, the convection with the full-fledged Navier-Stokes equation, and to do the do comparison actually.
So you want to continue with this thing, hopefully?
Yes, of course.